Section 5.2, example 21, absolute versus conditional convergence. So for each of the following series, determine whether the series converges absolutely or converges conditionally or diverges. So start with moving this. So now an absolute convergence means that the absolute value of this series converges and the series itself converges, then it's an absolute convergence. If the, how do we say it? If the function itself converges, but the absolute value of the function diverges, then it's just a conditional convergence. Only part of this alternating series converges and not the entire thing. So let's get into it. So let's start with the absolute value first. So us looking at the absolute value is basically us looking at this without this one. So we're going to take the limit as n approaches infinity of just the absolute value part. So that's going to be a 1 over 3n plus 1. And let's see. Let's use a limit comparison test. I think that's going to be an easy one. Limit comparison test. So with the limit comparison test, we're looking at another easier function that we could use to prove this. So what I say is, oh, actually with limit comparison test, we didn't need anything like that. We just needed a function that we could compare it to. So we're looking at b sub n equaling 1 over n. So b sub n equaling 1 over n. Then we're going to take the limit as n approaches infinity of this function 1 over 3n plus 1 over 1 over n. If we multiply both top and bottom by n, we end up with the limit as n approaches infinity of n over 3n plus 1. We divide both top and bottom by n, we get the limit as n approaches infinity of 1 over 3 plus 1 over n, which ends up going to 3. And because it goes to 3, it's not equal to 0. So either both of these converge or both of these diverge. So because of that, we have the limit as n approaches infinity of our other function right here, 1 over n. And we know that this diverges. Ooh. So this one diverges. So because of this, we have, I'm gonna spell the rest of it. So because of this, we have the absolute value diverging. So therefore, the sum of the absolute value of a sub n, I'll just write it like this part diverges. Which, okay, because it diverges, we still could possibly have a conditional converge. So because that one diverges, let's take a look at the other one. So the alternating one. So now let's look at the alternating series. So we have the alternating series, still looking at the same one, and goes from 1 to infinity of negative 1 n plus 1, 1 over 3n plus 1. So now we're going to compare b and b plus 1. So looking at b sub n, 1 over 3n plus 1. Okay. Looking at b n plus 1. So plugging n plus 1 in, we have 3n plus 4. And so we have this part here. We have b n plus 1 is less than b sub n. So now we can move on to the second condition of the alternating, what was it called? Alternating series test. So the second part is taking the limit as n approaches infinity, and then we're going to go up to 0. So the limit as n approaches infinity of 1 over 3n plus 1. And this ends up going to 0. Okay, so it's satisfied both of them. So this tells us here, so therefore the sum of a sub n converges, since the a sub n converges and absolute value of a sub n diverges. This tells us that this is a conditional convergence, or converges conditionally. So converges conditionally. All right, one down, one more to go. I don't know if we're going to have enough room here for this one, so let's move this one over here. All right, so we have this question here, the sum as n goes from 1 to infinity, cosine n over n squared. All right, so with this one, I know that this has, this is alternating because cosine is alternating. So we're going to look at the absolute value of these two. So earlier in this chapter, we did something called squeeze theorem. So squeeze theorem told us to look at negative 1 over n squared, which we know is going to be less than or equal to cosine of n over n squared. And because we're multiplying by a number smaller, this one's always going to be smaller than 1 over n squared. So based on this, based on squeeze theorem, so squeeze theorem, we know that, what was it? The limit as n approaches infinity of negative 1 over n squared was equal to 0, which is also equal to the limit as n approaches infinity of 1 over n squared, the positive one. Since those two were equal to 0, then we could say that the limit as n approaches infinity of cosine of n over n squared, this is also going to be equal to 0. So we have convergence here. And also we could use our limit comparison test. So because it converges here, we automatically know that it's going to be an absolute convergence due to, I believe it was the definition of absolute convergence or the theorem of absolute convergence. If it's already converging, then the entire thing converges. So therefore we have absolute convergence. So converges absolutely. Converges absolutely. And there we go. If you have any questions, please feel free to ask. Otherwise, bye.